Hello and welcome back to Psychology 301 Learning. This is Dr. Williams, and this is our third lecture in Unit 2 dealing with associative learning. Specifically, we're going to be talking about the Rescorla-Wagner Model of associative strength or associative learning. And this is a very specific lecture that deals with the use of mathematical modeling to describe changes in associative strength across trials. So before I start this lecture, I need to give you a little bit of background. In the 1940s through the 1970s, the early 1970s, there was a movement within learning to attempt to employ the use of quantitative models, mathematical models, to describe different types of learning phenomena. And this is the first one that you'll be exposed to. And although it sounds kind of scary, it's really not that scary. And in fact, it's kind of interesting and kind of cool. The idea that we can use mathematics to describe the trajectory of asteroids or planetary paths seems appropriate and commonplace in the sense that most people in the Western world are aware that we use math for those purposes, to describe the pattern of earthquakes, to understand the movement of oceanic currents. So there's a lot of behavior out there that has been described by math, but when it comes to describing human behavior by math, it can be a little bit intimidating. So this is just one version of this. I have to say that this idea of quantitative analysis of behavior has started in the 1940s, was very strong through the 1970s, but has continued. And today there is even a professional academic affiliation or organization called the Society for the Quantitative Analysis of Behavior. And so there's a small subset of people within learning who ascribe to this idea of mathematical modeling. That's tied directly to the kinds of behavior changes that we see in the laboratory. And so the Rescorla-Wagner model is one of the most successful versions of this quantitative analysis. So let's go ahead and get started. So the Rescorla-Wagner model was published in 1972 by Bob Rescorla and Alan Wagner. But in fact, the original model was published separately by these two professors. In the same year, Bob Rescorla and Alan Wagner published papers that they had been working on for quite some time, since the mid-60s, on a mathematical model that would describe how classical conditioning occurs from trial to trial. So how the power of the US gets transferred to the conditioned stimulus during classical conditioning. And they came out with papers the same year. And those papers were later shown to be the Rescorla model and the Wagner model, although they looked different initially, there were people who were able to demonstrate that they were virtually the same. And so the model became a single model, and it was labeled the Rescorla-Wagner model alphabetically. And this model has been one of the most robust mathematical accounts of learning in modern history. So let's talk a little bit about the Rescorla-Wagner model. It's basically, what is it? Well, it is a mathematical model that tries to characterize the nature of the process of classical conditioning as it occurs from trial to trial. So it describes how the power of the US to control behavior is transferred to a neutral condition stimulus on a trial-by-trial basis. So how much is learned, and what changes in terms of the power of the conditioned stimulus? How does that build from trial to trial? So it attempts to characterize the mathematics of how we learn with classical conditioning using mathematics. Now, before we look at the model, we are going to need some definitions so that when I talk about the model, you'll have a little bit better understanding of what we're talking about. Okay, so the first thing is this model is designed to account for the associative strength of the conditioned stimulus. And so we need to kind of understand what that is. So the associative strength is literally the power of the conditioned stimulus to provoke a response, a conditioned response. So if we're talking about a Pavlov's bell and salivation, the associative strength of the conditioned stimulus at the beginning, the bell at the beginning, is neutral. So it's zero. It has no associative strength. There's no association between the CS and the US. And that bell does not provoke, it doesn't elicit salivation. And so when we talk about associative strength, we're talking about the amount of behavior control or the power to control behavior that gets transferred from the unconditioned stimulus, the food powder, to the bell, the CS. So when we talk about associative strength, that's really what we're talking about. We're talking about the power to control behavior, the power to elicit a conditioned response. Now, another concept within the Rescorla-Wagner model is the asymptote of learning. And the word asymptote comes from math, and it means the maximum amount or the ceiling. And so when we talk about it, an asymptote, when we talk about learning, we're really talking about the maximum amount of learning that can happen, or the maximum amount of associative strength that can be imparted to the conditioned stimulus from the unconditioned stimulus. In other words, the power to control behavior, to elicit salivation from a dog, the maximum amount of power to actually elicit that response that gets transferred from the food to the bell. And so there's a maximum, there's a limit, there's a ceiling. That amount, how big that amount is determined by the amount of power in the US. So if you have really, really yummy food, like little bits of hot dog, for my dog Dixie, you'll have a lot of power to transfer to the CS because she loves hot dogs and they're very powerful in terms of eliciting salivation. But if you're talking about boring, dry little dog biscuits, she's not really big on those. So there'll be very little salivation available, very little associative strength available to be transferred because the US doesn't have very much power. So there's a direct relationship between how powerful the CS can be that's tied to how powerful the US is. So that's really what the asymptote of learning, you can call it the ceiling of learning or the maximum amount of learning that they'll ever do. The CS will never be stronger than the US. It will only impart some of it. And in the model, when we look at the mathematical model, that concept, that idea of asymptote of learning is represented by the Greek letter lambda. And this is a little lambda. That's what it looks like. And so there are lots of ways to describe this. I think it looks a little bit like a hatchet on its side or like a little lean-to, and this is the roof. That's helpful for me because it reminds me that it's the ceiling. So this is the maximum amount up here at the very top. That's the maximum on the roof of lambda, just as a little way of remembering it. Okay, now we're going to need these two concepts when we talk about the model. So let's talk about the basic concept that underlies the model, or the basic tenet of the Rescorla-Wagner model. The basic idea is that we only learn, or we only transfer, a percentage of the available associative strength of the US to the CS on any given trial. And as long as nothing changes, as long as the CS stays the same and the US stays the same, that percentage remains constant. Okay, so if you have a bell and food and a dog, you're going to transfer a certain amount on every trial. You're going to transfer a percentage of the total associative strength of the US to the CS. And if it's any less than 100%, then it's going to take several trials in order for them to learn and acquire this association. And that's what the basic idea of the Rescorla-Wagner model really is. So what you're basically doing is you're learning the same percentage on every trial, but that percentage produces a smaller and smaller amount because it's cumulative. So we're working toward 100%, and you only learn the same percentage every time. Now that percentage is tied to the conditioned stimulus, and it's tied to the salience of the conditioned stimulus. And that's a word a lot of people don't understand. The word salience means how noticeable it is, how novel it is, how attention grabbing it is. The more salient a stimulus is, the bigger the percentage that you learn on any trial. So if the dog has never heard the bell before, and the bell is loud and clear, they're going to learn that. It's going to define a large percentage, and they're going to learn a lot on the first trial, and so they might learn maybe 25% of the total associative strength available. But if it's a very quiet stimulus, something that you've heard many times, it's not very noticeable, it's not very meaningful to you, maybe you've habituated to it, so it's just not very salient, that percentage is going to be very small. Maybe you only learn 5% on each trial. So the important thing to remember here is that the percentage is tied to the unique, novel, interesting, and salient nature of your conditioned stimulus. That means you need to pick a really good conditioned stimulus if you want learning to happen quickly, okay? And so the more interesting it is, the more novel it is, the more unique it is, the faster you will learn on each trial. The more you learn on each trial, and as a result, the faster you will acquire the association. Now, typically we don't change the CS in the middle of an experiment. The CS is fixed. And so in the model, when we look at the experimental model, that value is, because it doesn't change and because it's fixed, it's a constant. So it's represented by the letter K, which is the letter that's used to describe, to write the word constant in Russian. So K, I'm making this up, but K stands for constant. I know it's misspelled, but it'll help you remember it, okay? It stands for constant. So we have a constant amount that's learned on every trial, all right? And so after each trial, we learn a little more. So if you're learning 10% and you have 100% available, on the first trial, you will transfer 10% of the power of the US to cause, for example, salivation or eye blinking to the CS. And then on the next trial, you'll learn another 10% of what's left over. So we're going to get into the calculations to give you an example of what this looks like. But what you learn on each trial is represented by the letter V. Now, I don't know why mathematicians feel like they need to have letters, Greek letters and alphanumeric letters, and in their, I think it just makes the mathematics easier to write. But with the Rescorla-Wagner model, every one of these pieces, lambda, K, and V, which are the big ones that they're like variables, they stand for something very real. They have a psychological reality. So when we go through this model, and I'll show you what the model looks like and we'll talk about it, I'll go back through and remind you of what each of these things are, because you can literally translate the model into a basic English sentence that makes sense. All right, so let's look at the model. Okay, here's the model, and I'm going to use my little cursor here to help point out what things are, okay? So remember that the goal of the model is to predict how much of the available associative strength is transferred to the CS from the US on any given trial. So this model is designed to talk about each trial independently. So let's start with this first component. So I'm using my cursor here, and I'm going to use a little pointer. So this first component here, this piece right here, okay, that piece represents what you learn on each trial, and it's represented using the letter delta. Now the letter delta means change, and V, remember, is associative strength. So we're talking about the change in associative strength that occurs on trial N. N equals the trial that you're on. So it starts with trial 1 and then goes to trial 2, trial 3, trial 4. So this whole piece right here represents what you learn on any given trial. So what you learn on any given trial is equal to, and you have this whole piece, this is the mathematical formula that describes what determines that change. So remember, I'm going to use my little cursor here again. The first thing that we have here is K. K is a constant and refers to the salience of the conditioned stimulus. The CS is what determines K. And remember, this is going to be a percent. It's a percent. How much of the remainder of this whole kernel is learned on each trial. Okay? So we have K is a percentage of how much associative strength will be transferred on every trial of what's left to learn, and that's determined by the CS. Okay? Now we have this last piece here. Let me turn this back on. I hope this is helping. So we have this component right here, and in this component is this is what we call what's left to learn part of the equation. So you're going to learn a percentage of what's left to learn. And what's left to learn is the combination of your lambda, which is always 100%. So we're going to call this 100 here, 100% minus this piece here is what you have already learned. So let me outline what those are. Here, I'm going to turn this off for a second and talk about them individually. The first thing that you're going to see is sigma. Sigma is a Greek letter. It means the sum of. And notice that what we're adding up here, the sum of all of the delta V's for n-1 trials. So if this is trial 1, then this would be n-1 would be trial 0. And there, you haven't learned anything on trial 0. But when you're on trial 2 or 3 or 4, let's say you're on trial 3, your n equals 3, then here you're going to have 3 minus 1. So it's going to be the sum of the delta V's from trials 1 and 2, just the first 2 trials. Okay? So what this adds up to, oops, here we go. This piece right here adds up to 100. So it's always, this is always 100, always 100. It's 100% of whatever there is, whatever the US will hold. So remember, what determines the actual strength of lambda? It's the US, and it's always going to be 100. Okay? And this piece here is just what's left to learn. So you're going to subtract what's left to learn from the 100, and what that gives you is what's left over. And you're going to learn a percentage of what's left over. Okay, so before we go any farther, what I'd like to do is go through an example so that we can see how this works. So let's start. First, we have to set some parameters here. So I'm going to put the model up here at the top. So here's our model. What's learned on trial 1 is equal to K, which is a percentage set by the CS, of 100% minus what you've already learned. And on trial 1, we've learned nothing because n minus 1 is 0, so we end up with 0. But we have to set the asymptote. We need to know what this is. And for our purposes, for the whole class, it's always going to be 100%. Now, Rescorla-Wagner and their research assistants have ways of determining what lambda is in absolute numbers. So a certain amount of shock is equal to a large number, a small amount of shock is equal to a small amount of a small number. And so they can actually work with real numbers, but we're going to just work with 100% so that we understand the model conceptually. So we have 100% minus what we've already learned, which of course on trial 1 is nothing. And K, we're going to set the salience value of K to 25%. So for every example that we do, the asymptote will always be 100%. It'll always be 100. And K, which is determined by the CS, is going to be 0.25 for this example. And so a salience value of 0.25 would be something like a yellow key light, not a super bright, but not a dim key light for a pigeon, or a moderate tone for a rat. And so now we're going to calculate, since we know what K and we know what lambda is, now we can begin to calculate how much of the associative strength will be transferred on each trial as we move forward. Okay, so let's start with this one. Here we go. All right, so here's our first trial. Again, the model's up here at the top, and now we're going to start plugging in numbers. So we're going to say delta VN for trial number 1, let me grab this, for trial number 1 is equal to, remember we said K is 0.25, so it'll always be 25%. We're not going to change it. It'll always be 25%. Lambda is always 100. 100 associative strength units, if you will. And here, the sum of all of the delta VNs from previous trials is equal to 0 because there haven't been any previous trials. So the amount of change that we're going to see in V, in the associative strength, is going to be 25% of 100 of the whole amount. So on trial 1, we're going to learn 25% of 100 minus 0. So 25% of 100 minus 0. So that one's pretty easy. So now let's look at what happens on trial 2. Okay? So this is trial 1 up here, and here now we have trial 2. So now we're going to look at how much of the associative change in associative strength will occur on trial 2. Here's trial 2. All right, so it's going to be 25%. It's always 25%. K is a constant, and it will always be 0.25 for this particular experiment. Lambda, in our examples, will always be 100%. Whoops. So there's lambda, and here's lambda. For us, it'll always be 100. And now we need to subtract from lambda what we learned on all the previous trials. Well, we've only had one previous trial. 2 minus 1 is 1. So what did we learn on trial 1? We learned 25 units of associative strength. Excuse me. And so we bring that 25% down here and plug it in here because that's what we've learned on the previous trial. We now say 100 minus 25 is 75 units are left. What's left to learn? 75 units of associative strength. And we're going to learn 25% of that. And when you do 25% of 75, you get 18.75. So on trial 1, we learned 25%. On trial 2, we're learning 18.75% because there's a smaller total. So what do you think will happen on trial 3? Well, on trial 3, you're going to have to sum, remember we're going to sum all of the delta V's from all the previous trials. So we're going to have to add 18.75 and 25. Excuse me. Allergies. Okay, so here I have 4 trials from this example. All right, here we have trial 1. Whoops, I didn't mean to do that. I'm sorry. Oh, that's weird. There we go. All right, there we go. Okay, here we have trial 1. We have trial 2. How much associative strength is going to be transferred on trial 3 and ultimately on trial 4. You could also have a 5, 6, 7, 8 until you are all the way up at close to 100 units. Trial 1. What is K? K for this example is 0.25, so we have the exact same example that we had in the previous slide. 0.25, 25% of 100 is 25. Trial 2, so now at the end of trial 1, the CS now has the associative strength of 25 units. For trial 2, the change on trial 2 will be 25% of the same 100, the total, lambda, which is here, minus the sum of the delta V's from previous trials. So again, we bring the 25 here, and we subtract 100 from 25 from 100, we get 75. Take 25% and you get 18.75. Now on trial 3, so now the associative strength that has been imparted to the CS is the sum of the 25 plus the 18.75, which is 43.75. Okay, so on trial 3, again, 25% K, same amount. Lambda, same amount, 100. Minus, now we have to add these two together and put those there. So now we have 100 minus 43.75, and then we take 25% of that, and it's 14.06. So on the third trial, we learn another 14.06 of the 100 units that were the total associative strength available. On trial 3, we have to add the 25% plus the 18.75, and we need to add that to the 14.06, which becomes 57.81. And when you subtract that from 100 and take 25%, you get 10.55. So on, pardon me, let's say we do delta V5, what is going to be the sum of all of the delta V's from the previous trials will be 25 plus 18.75 plus 1406 plus 10.55. And it continues for every trial that you hold from that point on. Okay, so one of the things that you'll notice is that the absolute amount of change that happens on each trial gets smaller and smaller. And I want to say, why is that? Well, it's because of the diminishing value of what's left to learn. Remember that it is this entire kernel here is referred to as what's left to learn. You're learning a percent of what's left. So if you think of this like 2 glasses of water and you pour 25% from glass 1 into glass 2, then you have to say what's left. Well, you have 75% left. And then if you only take 25% of that, you're going to get a smaller amount. So this amount keeps diminishing because the total amount of what's left to learn is getting smaller, but you're always learning the same constant amount. And in this case, it's 0.25. In other cases, I might say K equals 10. And then this value here is going to change and it would become 10. Or it could be 17. So the big change that will happen, lambda will always be 100, but I will give you K, and you'll then have to calculate using that K value in this position here. So if I said it's 10%, then this would become 0.10 for all of them. If I said it was 17%, that would be 0.17 for all of them. But it would be the same all the way down. Okay, so now that I've done that, I want to show you what it looks like when you plot these data on a graph. What happens when you plot all these numbers on a graph? Well, you get a special kind of curve. The amount that's being learned is going up, but it's going up at a smaller and smaller and smaller rate at each point. So I need to talk a little bit about learning curves. Okay, so learning curves can be divided into 2 big categories. The first one is whether or not the curve is accelerating or decelerating. Accelerating curves mean that that behavior is starting out low and increasing. And a decelerating graph means that behavior is starting out high and decreasing. Okay? So whenever you see a learning curve, the name of a learning curve, you're going to look at whether or not it says accelerating or decelerating, and you're going to know whether or not the behavior is increasing or decreasing. Now, the other category is whether or not that change that's happening, this increase or decrease, whether or not it's happening faster and faster or slower and slower. Positively changing curves are behaviors changing. It starts out slow and gets faster and faster as you move. Negatively changing curves, the behavior is changing, but it starts out very fast and then the change happens slower and slower and slower. So the result is that you get one of these 4 learning curves. Okay, so we have accelerating and decelerating. remember, let me get my little arrows here. Accelerating means that the behavior is going up. Decelerating means that it's going down. So here, both of these two curves, the arrows are going up because behavior is accelerating. It's going up, it's increasing. Decelerating, both of these curves are going down. They start out high and they're dropping. And so you get decelerating curves here. And now we can look at positively and negatively. Positively accelerating curves start out slow and get faster and faster as you go. The slope of the line is very low here and then gradually gets faster and faster. The same is true for the decelerating graph. It starts out slow and then gets faster and faster and faster as it drops. So this is a positively accelerating curve here, and this is a positively decelerating curve here. Negative acceleration means it starts out very slowly and then gradually increases. So they start out fast and slow down as they go. Negatively decelerating curves also start out very fast, a precipitous drop, and then they slowly taper off. So while both of these curves are decelerating, this one is decelerating in a positively decelerating format, and this is decelerating in a negatively decelerating format. And the same is true for acceleration. So we end up with 4 learning curves. Positively accelerating looks like this. Negatively accelerating looks like that. Positively decelerating looks like this, and negatively decelerating looks like that. So when we go and look at the graph for the Rescorla-Wagner model, you'll notice that the biggest changes happen first. Let's go back up here and look at this graph first. Oops, there we go. Notice that the biggest change happens on the first trial. Then it gets a little smaller and a little smaller and a little smaller. So because we're adding these up, because it's cumulative, it's an accelerating curve. You're getting more and more control over behavior. You're getting more and more behavior out of the subject with the CS. In other words, the bell is producing more and more salivation because we're adding up the associative strength. It's getting stronger and stronger and stronger, but it's doing so in a way that starts out very fast and then slowly begins to slow down. So we have, it's accelerating, and it's accelerating very quickly at first and then slowing down. So the curve that we get looks something like this. And this kind of curve is a negatively accelerating curve. It is going up. Here, let me put this on here. So let me show the direction of the curve first. Boop. So we have, it's increasing. And it's increasing very fast at the beginning, and then it's slowly tapering off. If you look at the what's left to learn, you have a lot left to learn here, and you have a very little amount left to learn here. So the associative value that the conditioned stimulus has is growing, but it's growing at first fast and then slower and slower, so that makes it a negatively accelerating curve. Okay, so the Rescorla-Wagner model, let me back up. The Rescorla-Wagner model predicts that learning will occur like this. And when we actually measure classical conditioning, that's exactly the curve that happens from trial to trial to trial. So not only is this a prediction, but the prediction has been shown to be very accurate in terms of the way in which classical conditioning unfolds. Now, the Rescorla-Wagner also makes certain predictions. It says that when, here, let me put this back up here. Now remember, this little piece here is the sum of all the previous trials. And so this is how much power or how much associative strength your CS has. And that will continue to grow when it's less than the asymptote. When this is less than 100, you will always have a little bit left over, and it will continue to grow at whatever that constant percentage is. The same thing will decrease if for some reason it's larger than the asymptote. So one of the things that they've done is they say, okay, well, what happens if the asymptote were to change and be less, if the US were turned down, if we suddenly shifted it to less shock or less preferred food for the US. And the model predicts that it will, what's left to learn will actually decrease when it's larger than the asymptote. And that's exactly what happens when you run the experiment, which is pretty cool. And if for any reason what's left to learn is equal to the asymptote, so if you have when what's left to learn is that when the sum of all of the delta V's is equal to the 100, then when you take lambda minus the sum of all of these, you get 0 and you get no change. And so that's actually what happens with the Rescorla-Wagner model. So it makes some very specific predictions, and yet all three of those predictions are upheld when conducted on real organisms. So, for example, I'm going to skip. So, for example, the Rescorla-Wagner model actually predicts a phenomenon called blocking. And we know that blocking occurs, but the Rescorla-Wagner model actually predicts it. So when we talk about blocking, I'll come back to the Rescorla-Wagner model and point out that this is actually predicted by Rescorla-Wagner, and when conditions are set up, you actually get the blocking effect. The same is true with extinction. It can predict Pavlovian extinction, and it can predict Pavlovian inhibition. Here, I'll talk about blocking here. This is the over-expectation experiment. It predicts this as well. So in phase 1, you have two stimuli. You have stimulus A and you have stimulus B. And A predicts one pellet and B predicts one pellet. So maybe this is a light and this is a tone. And so they see the light and they get food. They hear the tone, they get food. And they do that for a while until the classical conditioning starts to kick in and A becomes powerful enough to predict the pellet. Okay, so you get this association that A is predicting one pellet and B is predicting one pellet. You then move to phase 2 where A and B are presented together. And when A and B are presented together, an over-expectation is created. So if A equals one pellet and B equals one pellet, then in phase 2, A plus B should produce two pellets. But it only produces one pellet. And then in phase 3, they go back and they test A and B, and what they find is that the associative value of A and B decrease because it had a higher expectation, an over expectation in phase 2. When that over expectation is canceled by delivering only one pellet, not two, each of these two stimuli lose some of their associative strength and you get less responding to each of them. That's pretty interesting. Correctly predicted by Rescorla-Wagner. Finally, the Rescorla-Wagner model is not perfect. It doesn't predict everything. There's something called latent inhibition, in which you pre-expose a stimulus before you use it in your classical conditioning experiment. So let's say we take the bell with Pavlov's dogs and we bring the dogs into the lab and we ring the bell, but nothing happens. And we ring the bell and nothing happens. And we ring the bell and nothing happens. And we do this day after day for many, many trials. After a while, the bell becomes meaningless. It predicts nothing. And so it becomes kind of a neutral stimulus, but neutral in a different way. Now it's not just novel, something you've never seen before, but now you have a history of it predicting nothing. When you go to use it in the Pavlov dog experiment, you ring the bell and present food. It actually takes that dog longer to learn about the bell than it does a dog that's never heard it before. And the argument is, although Rescorla-Wagner does not actually predict that this will happen, if you assume that pre-exposing that stimulus actually reduces its salience or its K value, if you assume that through pre-exposure you reduce the salience, or the value of K gets smaller in the Rescorla-Wagner model. And when you do that, learning slows down. So although the Rescorla-Wagner model does not actually explicitly account for latent inhibition, if you assume that pre-exposure reduces salience, it therefore must reduce the K value. And if the K value goes down, then you're going to get slower learning. So the model is not inconsistent. And this is you have to make a little leap of faith, but it's a very little leap of faith, and then the model is completely consistent. So the Rescorla-Wagner model is a very robust model and has been used now for decades to understand classical conditioning. So I'm going to stop there, and we'll pick up in the next unit with Unit 2D. All right, we'll see you then. Have a good day.